Hi everyone, let's continue with sessions 8.6. So right now I want to recall our growth rate sequence. So the slowest is the logarithmic function, and then we have the polynomial, and then we have the exponential function. Then the factorial is actually faster than exponential function. The fastest is n to the n. So here is the growth rate, okay? So keep this in mind. Let's continue with the following problems. So remember here we're determining whether an alternating series diverges or converges absolutely or converges conditionally, okay? So what is our first step? Do you remember? The first step is to compute the limits of the sequence. Okay, so the limit of the sequence, we have k factorial and k to the k. Which one grows faster? K to the k. So if the denominator grows faster, then this quotient goes to 0. Okay, so if we get 0 here, it means divergence test tells us nothing. We need to continue to step 2. So step 2, we want to compute the series of a sub k. Does this guy converges or not? Okay, and then look at this series. Well, this series, k to the k over k factorial, what test shall we use? Well, can you see it contains k factorial and k to the k? Then we should use ratio test. Okay, so ratio test. What is ratio test? We compute R. R is the limit of a sub k plus 1 over a sub k. And yeah, here our a sub k's are positive, so we don't need absolute value. Okay, so that is, we replace k by k plus 1. So this is k plus 1 to the k plus 1. And the denominator is the same thing as before. Okay, and then we want to combine in, so we can make it look nicer, okay? Make it into a fraction, and we want to split the factors. How do we split k plus 1 factorial? So keep in mind, our goal is to cancel with some of the terms downstairs. So here, we split as k plus 1 and times k factorial. So this is how we split this term. Okay, the bottom we can split as k plus 1 and k plus 1 to the power of k. Right? We can split a factor. And then for k factorial, we put it downstairs. Remember, a over b over c over d is a over b times d over c. And k to the k, we put it upstairs. Okay, so what can we cancel now? We cancel k to factorial. We can also cancel k plus 1. So what do we get? So you can see the remaining factors, they are all to the power of k. So we can combine them together. Okay, so what is this guy? When k goes to infinity, the inside goes to 1, and the outside goes to infinity. So 1 to the infinity, this is indeterminate form. Okay, so for indeterminate form, we're gonna use L'Hopital's rule, and because you see k in the exponent, we need to compute the ln. So let's see, the limit k goes to infinity of ln of r is, so that is ln of k over k plus 1 to the k. So you can see we can move the k in front of it, so we can bring the exponent down. Then we have k ln of k over k plus 1. Well, when k goes to infinity, this is like infinity times 0. What do? In order to use L'Hopital's rule, we want to get either 0 over 0 or infinity over infinity. So that means we should move one of the factor downstairs. But we don't move the ln because it's so big. We don't want to move it. Let's move the k. But when we move it downstairs, you don't just put the k, you should put 1 over k. So they are equal. Alright, so now we have, when k goes to infinity, we have 0 over 0. We can use L'Hopital's rule. So L'Hopital's rule, that is the derivative of the top. But I don't want to do quotient rule. So let me use the property of ln. And we write it as this. So we're going to differentiate this guy. And over 1 over k derivative. So now what do we get? Derivative of ln of k is 1 over k. Derivative of ln of k plus 1 is 1 over k plus 1 times u prime. But u prime is k plus 1 prime, which is also 1. And then we have the derivative of 1 over k is negative 1 over k squared. Okay, what is that? Well, let's simplify it. We take the common denominator, which is k plus 1. Then the first factor, we multiply by k plus 1. The second factor, we multiply by k. And the bottom stay the same. So you can see we have k and k cancel. So we have 1 over that. What is that? So 1 on top, and k plus 1 in the bottom. And the minus, we can think of minus 1 is downstairs, and k squared is actually upstairs. Okay, so what is this guy? And you can see here, when k goes to infinity, we look at the dominant terms. So the dominant term of numerator is k squared. The dominant term of denominator is negative k squared. So that is the limit, k squared over negative k squared, which is negative 1. Is my r equals to negative 1? No, be careful. Okay, our r is e to the ln of r. So that's why so ln of r is actually has limits minus 1. So my r is 1 over e. So 1 over e is less than 1. Okay? Yeah, if you use the minus 1, you see, you get lost, right? Get stuck. Because r should be greater or equal to 0. Okay, and if the absolute value of r, if r is 1, then the test is inconclusive. Okay, so here, because r less than 1, then we know the series a sub k actually converges. Because the series of a sub k converges, so we say the alternating series converges absolutely. Alright, so this is the solution of part D. Okay, let's continue. So let's continue. Look at E. So we start with what is okay. Let me change the problem to make it more challenging. Okay, so let me make this to be 3. Okay, so what happened now? Well, what happened is, well, because now it's 3, so your AK should be the absolute value of negative 3 to the k plus 1, e to the k, and k squared, and 2k plus 1 factorial. When you look at the absolute value, so negative 3 to the k plus 1 actually becomes 3 to the k plus 1. and we have e to the k squared all over 2k plus 1 factorial. Okay, so first step, limits of the sequence. And you can see the numerator, we have exponential function and the power function, but the denominator, we have factorial. So the factorial is grow faster than the exponential functions and polynomials. So that's why the denominator grows faster. The limits of the quotient is 0. And then the divergence test tells us nothing, so we have to go to step 2. So step 2 is to compute the series of a sub k, does that converges or not. And here, because you can see the series contains exponential function and the factorial, so we should use ratio test. Ratio test R equals to limits k goes to infinity of a sub k plus 1 over a sub k. What is that? Alright, so a sub k plus 1 means whenever you see k in the expression, you replace that by k plus 1. Then k plus 1 actually becomes k plus 2. And e to the k plus 1, k plus 1 squared. Okay, here 2 times k plus 1 plus 1. So don't forget the parentheses. So this is so important. Okay, everybody? Alright. Let's continue. And the denominator will stay the same. So, we have 3 to the k plus 1 and times e to the k times k squared and 2k plus 1 factorial. Okay. So let's see. Our goal is to split and cancel some terms. So you can see 3k plus 2. So 3k plus 2, we want to cancel with 3k plus 1. So how do we split? We split as 3k plus 1 and 3, right? E to the k plus 1, we want to split with e to the k. So we also split as e to the k times e. And k plus 1 squared, just leave it like that. Don't multiply out. How about the bottom? The bottom, it actually equals to 2 times k plus 2 plus 1 factorial. So this is like 2k plus 3 factorial. How do we split that? Well, we can split this as 2k plus 3, next term 2k plus 2, and next term 2k plus 1, and we stop here because 2k plus 1 factorial is what we want. So that's why we stop here. Factorial. And then 3 to the k. Okay. So 3 to the k plus 1 stay downstairs. E to the k stay downstairs. K squared stay downstairs. And then we have 2k plus 1 factorial upstairs. So let's cancel. What can we cancel? 3 to the k plus 1, e to the k, 2k plus 1 factorial. Okay, let's see what is left. So we have 3ek plus 1 squared. The bottom we have 2k plus 3, 2k plus 2, and k squared. Alright, what is the dominant term of the numerator? So dominant term of the numerator that is 3e times k squared. How about dominant term of denominator? Well, that's 2k times 2k times k squared. So that gives us 4k to the 4th. So this limit equals to 3ek squared over 4k to the 4th. And we can see k squared and cancel with the 4. We still have 2 left in the denominator. So when k goes to infinity, this is 0. If we get 0, what do we say? Because it's less than 1, if the ratio r is less than 1 by the ratio test, okay, we already say ratio test. So by the ratio test, our series converges. So because our series converges, then the alternating series, okay, so actually this is the alternating series, okay, will converges absolutely. Okay, everybody? So that is this problem. Let me ask you, if you don't get 0, let's say if you get 2, then what happened? If you get 2, then because it's greater than 1, you say the series diverges, and then you go to step 3. In step 3, you say, because our sequence is decreasing. By the way, this is sequence is decreasing. Some students put, oh, the series. Series is not decreasing. Your series is, you're adding more and more and more terms. So you're always increasing. But the alternating series might be sometimes increase, sometimes may decrease, okay? But we don't say the series decreasing or increasing. So series is actually a limit of the sequence of partial sum, okay? So the series is either a number or it's infinite. Okay, it's either converge equals to a number or it's either diverges. Okay, it's like infinity. All right. So we say the series sequence is decreasing by the alternating series test. Okay. But alternating series test, our alternating series converges. So that's why the alternating series converges conditionally, okay, if this is 2. Okay, so that is example E. All right, so let me delete this, okay, because I don't want you confused and think this is the part of the solution of this problem. Okay, all right, what's next? Okay, so here I give you a table so that you can compare the special series and the test. Okay, so the special series are the geometric series, the telescoping series, and the P series. Okay, the convergence conditions for geometric series is when the absolute value of the ratio is less than 1. Condition for divergence is when the absolute value of the ratio is greater or equal to 1. And comment, if the absolute value of the ratio less than 1, then the series actually converges to the first term of the series over 1 minus the ratio. And the P series, we have converges if P is greater than 1, diverges if P is less than or equal to 1. Why? If you can remember, 1 over x is like the boundary. It diverges. So 1 over x squared, 1 over x squared is actually smaller than 1 over x when x is greater than 1. So that's why when it's smaller, then it converges. And then 1 over square root of x, so 1 over x to the 1/2 is actually bigger than 1 over x when x is greater than 1. So that's why it diverges. So here, if P is bigger than 1, then our series is actually smaller than 1 over x. Okay, so that's why we have converges. Okay, so you can see this number and this number is kind of flip. So keep that in mind. And then for each test, we talk about the divergence test. So that's why the first step, you always compute the limit of the sequence. If it's not 0, then we get the series diverges. Okay? But if the limit of the sequence is 0, then we need to go to the second step. Second step, you're going to look at all the other tests. You look at integral test, ratio test, root test, and comparison test. And integral test, you have to mention our function f satisfy the conditions continuous, positive, and decreasing. And if the integral converges, then the series converges. And if the integral diverges, then the series diverges. However, the value of the integral when it converges is not the value of the series. We just know they converge at the same time or diverge at the same time, but we don't know what number they converge to. Okay, the numbers they converge to are different. Okay, and then we have the ratio test. You use ratio test when you see the terms like k factorial, k to the k, and a to the k. Okay? And it converges when the r is less than 1. It diverges when the r is greater than 1. So when r is 1 is inconclusive, it means you used the wrong test. So try other tests. The root test, you use root test if everything is to the power of k. So for what I just said, I already included in the maps. Okay? I mean these maps. Okay, it gives you first step, second step, and when to use integral test, when to use ratio test, when to use root test, when to use limit comparison test. Okay, so follow that map. And the root test, the criterion is similar. If it's smaller than 1, converges. If it's greater than 1, series diverges. If it's equals to 1, you use the wrong test. Try another test. Okay, so comparison test, we have the big guy and the small guy, and we know if big guy converge, then the small guy also converge. If the small guy diverge, then the big guy diverge. Okay? And the limit comparison test, when our series behaves like a p-series eventually at the tail. Okay? And then you compute the limits L. Okay? And if L is a finite number, and if your series b sub k converges, then our a sub k also converges. Okay? So, and if b sub k diverges, and our series also diverges if the limit equals to a non-zero finite number. Okay, but if it's 0 or infinity, then you just use the big guy converge implies small guy converge, small guy diverge implies big guy diverge. Use this criterion. Okay, and then in sections 8.6, we talk about the alternating series. So that's why for the alternating series, instead of 2 steps, like what we did before, we have 3 steps. Okay, it's like you fail to save the princess, or you save the princess and she wants to be your girlfriend, or you save the princess but she doesn't want to be your girlfriend. That's sad, right? So you follow the steps. If the second step you get the series of a sub k converges, then you say the alternate series converges absolutely. If the series of a sub k diverges, you actually will go to step 3. So step 3, you say the criteria, the hypothesis of the alternate series test. You say a sub k is decreasing, so the sequence is decreasing, not the series is decreasing. So I saw some students put a sum there. No, don't do that. The sequence is decreasing, not the series. Okay, the series we can only say converge or diverge. Because a sub k is decreasing, and also because the limits of a sub k is 0, which we already show it in step 1. Okay, so those are the 2 hypotheses of the alternating series test. Okay, then we say by alternate series test, our alternate series converges. So that's why it converges conditionally. Okay, so yes. And the absolute convergence implies convergence because we know the series of the absolute value is the big guy. And the series itself is a small guy. So this is the big guy. And this is the small guy. So that's why if big guy converge, then small guy converge. If small guy diverge, then big guy diverge. So far, so good, everybody? Are you okay with why the series of the absolute value is the big guy and the series of the AK is small guy? Because let's say we have a series 1 plus 1/2 minus 1/4 plus 1/6 and minus 1/8, this guy. Okay, so this is the series and some terms are positive, some terms are negative. Then we know this guy, when we compute the absolute value of that, it should be less than equal to when we compute absolute value of each of the terms. So that become 1 plus 1/2 plus 1/4 plus 1/6 plus 1/8. And then this is the series of the absolute value of a sub k, and this is the absolute value of the series of ak. So that's why the magnitude of that is less than equal to the series of absolute value of a sub k. That's why this is the big guy and this is the small guy. If the big guy converge, it means this sum is a finite number. Well then, because this guy is less than equal to a finite number, so itself, the series of a sub k is also finite. Alright? Okay, and please keep in mind here, I also put the absolute value here. Okay, you can see I also put the absolute value here because I want to show you is the magnitude that is less than equal to the series of absolute value of a sub k. Because if I don't use the absolute value, it could be a negative number, but the magnitude could be big. But with the absolute value, I also emphasize that it's the magnitude. The magnitude of the series. The series can be negative numbers, okay? But the magnitude of it is bounded above by the sum of the absolute value of a sub k. Alright. So if you have more questions, please feel free to ask me through emails or visit our online office hours. So this is all about chapter 8. Okay, bye.